Hello everyone. In the last two lectures, we discussed about the introduction to the phase diagram as well as about the phase rules. Basically, a phase diagram represents the existence of different phases of a system under equilibrium and the phase rule which relates the possible number of phases, the constituents and the degree of freedom in a chemical system. A phase diagram is the graphical representation of a physical state of substance under different conditions of temperature and pressure. It is actually a collection of solubility limit curves. It is also called the equilibrium phase diagram that represents the relationship between temperature, compositions and quantities of phases at equilibrium. The important informations, the useful information which we can obtain from the phase diagrams are uh, shown in this slide. It shows phases present at different compositions and temperature under slow cooling conditions. It indicates the equilibrium solid solubility of one element or compound in another. It suggests the temperature at which an alloy starts to solidify and range of solidifications. It signals the temperature at which different phases start to melt. The amount of each phase in a two-phase mixture can be obtained. The phase diagram can be broadly classified into two groups depending on the number of components present in the particular systems. These are called unary diagrams and binary diagrams. In unary diagrams, there is a single component is present in the systems, whereas in binary diagrams, there can be two components present in the systems. There are also three component systems such are called the ternary diagrams, but in your syllabus as well as in this lecture, we'll be only discussing about the unary diagrams and binary diagrams. In this slide, you will see a simplified unary diagrams, which is a one component systems. It is a simple two-dimensional depiction of the phase changes as temperature and pressure changes. Here you can see on the y-axis there is pressure variations, whereas in x-axis there is a temperature variations. Depending on that, we can see there are different phases are present in these particular diagrams, and you see the solid state here, liquid states here and gaseous state here, and the changes between two phases happening at a particular temperature, also at different pressure values, and these are the common terms which you already known about these melting, freezings, vaporizations, sublimation, etc. So this one you can relate to the water components. For example, you can see the water components which is having the ice states, the liquid water state as well as the gaseous form. So these three states are can be found in equilibrium at one point, that is called the triple point here. So this at this point that is represented as A in this diagram, there are three phases coexist and as the invariant points. So now we can consider what phase rules here. So according to the phase rules, the degrees of freedom of this particular point, the triple point, can be F is equal to C minus P plus 2, right? In this case, there are three phases coexist at this point, so that if you substitute the values here, see it is a single component system, so C is 1, so 1 minus 3 plus 2 will be 0. So that means at this particular point the degrees of freedom is 0. That means that is only happening at a one particular temperature as well as the pressure values. We cannot fix any of these values. So you don't have a freedom to fix the temperature at which we can bring this triple point. Also, we cannot define at what pressure we can obtain this three phase equilibrium. Also in this diagram, you can see there are two phase coexistence. For example, at this point B and C, there are two phases. At B, the liquid and gaseous state are found to be at equilibrium, whereas in C, the solid and liquid phases are found to be coexist in equilibrium. So if we substitute the phase rule here, the C minus P will be 2. So 1 minus 2 plus 2, it will be 1. That means in a two phase coexistence, we have a 1 degree of freedom. That means we can either choose temperature or pressure so that the other will be automatically fixed. So we can choose the temperature at which this can be coexisted. So provided the pressure will be fixed. The pressure value, we cannot choose the pressure value. We can either choose pressure or temperature. At this point D, there are only single phase. So this represents the gas state. So that means in a single phase system, if you substitute for the phase rule, the C minus P will be 1. So 1 minus 1 plus 2 will be 2. That means here you have the freedom to choose both temperature and pressure, which can be varied. Still the system will be at a equilibrium state in a single phase region. So in a single phase region, you have the freedom to vary both temperature and pressure. Still the system will be exist in the equilibrium state. If the system consists of only two components, the equilibrium phase exist is depicted as binary phase diagram. For most systems, the pressure is kept as a constant, probably at 1 atmospheric pressure. Thus, the independent variable present will be the temperature and compositions. Since there are two components, we can have composition as one variable system along x directions and temperature as another variable along y directions. We have seen similar picture in the earlier lectures. So the two component system can be a mixture of two metals, for example cobalt nickel, or it can be a metal and a compound, for example Fe and Fe3C. It can be two compounds. The two component systems again classified based on extent of the mutual solubility. Since there are two different components, which can some of the components which mostly will be completely soluble in liquid, and only in some cases it will be completely soluble in both liquid and solid phases. Such systems are called the isomorphous systems, where the particular components will be completely soluble in both liquid and solid state, which is an ideal case, because most of the cases the components will be completely soluble in liquid, but it is not so completely soluble in solid phase, and that is the general conditions. And the second class, where the components are completely soluble in liquid and which has got limited solubility in solid phase. So there are two type of binary phase diagrams. One is called the isomorphous phase diagram, which is an ideal case where the components are completely soluble in both liquid and solid, whereas in general systems it can be completely soluble in liquid phase and limited solubility in solid state. And the second class of systems are generally called the eutectic systems. The extent of solid solubility in a two component system can be predicted based on Hume-Rothery conditions, and if the system obeys these conditions, then there can be a complete solid solubility. So these are the conditions. The first one, the crystal structure of each element of the solid solution must be of same. For example, it has to be a cubic structure. If both component has to be a cubic structure. The second condition is the size of atoms of each two components must not differ by more than 15%. So that means the sizes of the atoms should be comparable. The third condition is the elements should not form compounds with each other. That is, there should not be no appreciable difference in the electronegativities of the two elements. and the final condition is the element should have similar valence. The valency of two should be same or similar. In this slide, you will see the isomorphous binary systems. As we explained earlier, it has got a complete solid solubility of two components, both in liquid as well as in solid phase. So that means this has to satisfy the Hume root 3 conditions we described in the last slide, and it has got three different phases, and this is the liquid phase, and this is the solid phase, and this region separate these two single phase region where the liquid plus solid state found to be at equilibrium state. Now we want to describe the regions of single phase and two phase equilibrium and various lines that separate in the phases boundary. The liquidus line you see here is the line that separates the single phase liquid from liquid plus solid phase, whereas the solidus line that represents the boundary that separate the regions between the liquid plus solid phase from the solid region. We are fixing the pressure and temperature we are fixing the pressure. In this case we are fixing the pressure so that there is only two variables, that they are the temperature as well as the compositions. Definitely since we have two components, there will be composition as one variable, and we describe as we described in previous lectures, along x direction there are the percentage of composition of this B is varying, and at A the percentage of composition of B is 0 and keeps increasing, and at B it is pure B, can be pure metal B at this point. So 100% B, there is 0% A. Now we can consider what are the equilibrium conditions as well as what are the degrees of freedom in the single phase region as well as in the two phase region. For the single phase region, it can be liquid or solid according to the phase rule. This is the modified phase rule because the pressure is found. We fix the pressure so that the phase rule is F is equal to C minus P plus 1. And since there is only a single phase, this will be 2. That means both temperature and composition of the phase can be independently varied within the limits in a single phase region. So we can vary either temperature, both temperature and compositions, so that still the system will be found to be in equilibrium. In a two phase region, this will be C minus 2, this will be 2, so that the degrees of freedom is limited to 1. So that means here we can have, there are three variables. In this case there are two, we have three variables. The variables are the temperature, then composition itself there are two. One is the composition of the liquid phase, the second one is the composition of the solid phase. So as F is equal to 1, only one of these we can choose either one of these three. So we can either choose temperature so that the composition of liquid phase, for example here in this line you see the line connecting this Y and this is Y and V. So here we fix the temperature value is fixed, so that the compositions, this is coinciding at the point U here and V at this point, U on liquidus line and V on solidus line. So the composition is fixed. The composition corresponds to this point is U dash, whereas this one, for this V, the compositions corresponds to the solid phase, that is fixed to V dash. So we can either choose any of these three variables. Now that we know the composition of the two phases, now we need to find out how much of each phases exist at the given temperature. So the ratio of two phases present can be found using the special rule that is called the tie line based lever rule. So here is the composition of liquid phase Composition of liquid phase, and here is the composition of solid phase. The line that connect these two points, that is called the tie line. This is the horizontal line where we establish a thermodynamic equilibrium with respect to temperature. So this is an isotherm line, actually the tie line, which is happening at a constant temperature. At a point in the phase diagram, the phases present and their compositions along with the relative fraction of phases can be found out using this particular tie line based lever rule. So for that, we need to consider the procedures as we discussed here. First we draw the horizontal line, that is the UV, that is called the tie line, that is parallel to this axis, x-axis, and then we draw perpendicular and draw from this point to the composition axis, and that those 2 points we marked as U dash and V dash, where the U dash represents the composition of liquid phase and V dash represents the composition of solid phase, as intersection U meets liquidus states and V meets the solidus line. In the two-phase region, that is this liquid plus solid region, we want to know whatever percentage of solid we have and whatever percentage of liquid we have. Let this capital X represents the composition of alloy of our interest. The fraction of solid that is present in the X compositions is of a liquid is given by the that of the liquid minus composition of alloy at that particular temperature divided by entire composition range inside that two phase field. In other words, the relative amount of phase that is computed by taking the length of the line from overall compositions to the phase boundary for the other phase and dividing by the total tie line length. So in this figure, we can find out the relative amount of liquid by using this formula, that is this is CV. CV is related to the solid phase. That line represents the length of tie line from overall compositions, that is from this point, that is C overall composition, to the phase boundary for other phase. So for liquid we need to consider other phase is solid. So this is the CV divided by the total length, total tie length. So that is the relative amount of liquid present. Similarly, if you want to know the relative amount of solid phase present in this particular alloy at that particular temperature, that is corresponds to CS, that is computed by taking the length of tie line from the overall composition, that is from C to the other phase, that is since we are considering solid to liquid, so that is CU or UC divided by overall tie length. Now we discuss about eutectic system. So the eutectic is a Greek word that means low melting point. A eutectic reaction is a three-phase reaction by which on cooling a liquid which transform into two solid phase at the same time. So it is a phase reaction but a special one. For example, a liquid alloy become a solid mixture of alpha and beta at a specific temperature. So this is happening at a particular specific temperature. So this side you see the liquid phase, liquid tin, and so this is a specific example, one of the most important specific example for the eutectic reaction is the tin lead. So which is this is the particular alloy which is used for the soldering. For soldering we use this particular alloy, that is tin and lead, at a particular combinations, and that is corresponds to the eutectic point. So this is the in this eutectic reactions you can see that this is this liquid tin and lead state which is transformed into solid tin and solid lead at a particular temperature at this particular point, and that is called that kind of reaction is called eutectic reactions. So this is a special one because this is happening at this melting is happening at lower melting point. So the melting point for the tin is given here, that is 327 degrees Celsius. At that temperature it becomes liquid. So the melting point for tin is given as 232 degrees Celsius. But this is happening at a low melting point when compared with these two. Lower than these 2 points, this alloy melt at this particular point. So such point, this point is called the eutectic point, and such reactions are called eutectic reactions, and the system exhibiting this kind of behavior is known as eutectic systems. In this particular example of tin lead, we can see that the liquid composition of at this point, the liquid composition of is this liquid composition, this phase having a weight percentage of 62 percentage of tin, and it is transfer and that is corresponds to alpha. At this point the alpha is found to be, alpha is corresponds to this point, the solid lead point, that is corresponds to uh, 18 weight percentage of tin, and beta is corresponds to 97 weight percentage of the tin. So this value you will understand from the next slide, because this diagram is oversimplified diagram which does not shows the alpha and the alpha plus beta separations. So the alpha corresponds to the pure tin and beta corresponds to pure tin, and there is a separation between this pure tin, the pure tin's solid as and the solid tin plus solid lead area. So that is not shown in this particular figure. So in a eutectic system, there is always a specific alloy known as the eutectic compositions that freezes at a lower temperature rather than the any one of the compositions temperature. Okay, we'll go to the next slide. So this in this slide, this is the binary eutectic systems, where you can see that this there are we can see different phase regions. So this is alpha corresponds to the pure pure tin region, pure tin, yes, pure tin region, and beta corresponds to the pure lead region, and there is this region is separated from this region, that is the composition of alpha plus beta, that is having the solid tin and solid lead composition is here. So this is a solid solution, but it is not completely soluble. These two solids are not is not a perfect solutions, and this is L plus alpha, that is corresponds to the liquid phase. This is the pure solution. The perfect solution is formed here of this lead and tin at this in this region, that is separated from this alpha by L plus alpha region, and there is also L plus beta region. So basically there exist three single phase regions, the L, alpha and beta, and there also exist three two phase regions, that is this L plus alpha, L plus beta and alpha plus beta. And there is still three two phase region that are separated by a horizontal line. So these two phase regions are separated by a horizontal line and corresponds to the eutectic temperature. So this is happening at this eutectic temperature. So this is what we call the tie line. Below eutectic temperature, at this here, the material is fully solid for all compositions. The compositions are relative amount of phases can be determined using tie line and lever rule, as we discussed earlier. The compositions that are on the left hand side of the eutectic compositions are known as hypoeutectic compositions. This side, this is called the hypoeutectic compositions, while those compositions on the right hand side of the eutectic compositions are called hypereutectic compositions. So the hypoeutectic compositions means it has got uh, less composition of A. So in that in the previous example, that tin, less composition of tin when compared with the eutectic compositions, whereas the hypereutectic compositions means it has got more amount of which one, the B, more amount of B, that means in the previous example lead. So this is having more B means B compositions mean it is a hyper eutectic compositions. If it is less than this one related to the eutectic composition, if it is less amount of B compare with this one the eutectic composition, that means hyper eutectic compositions.